everybody. Thanks for being here. I'm Michele Giusto from Data Reply. I'm here with Julien Genovese, also from Data. In this session, we will try to explain you why, from our point of view, it is important to look at data in a graph way, in a way in which we are not anymore just focused on tables on a tabular format, but more stressing the idea of getting data that are connected. From our point of view, in fact, the idea of looking at the relationship that exist between data is a great plus for discovering more from data, for improving the analytical processes, instead of just going with the traditional way, the tabular format that with which we are all used normally, but that can be improved by looking at the connection. When looking at connection, we really believe that they are more or less everywhere. Just some example. If you look at an e-commerce, basically there are connection everywhere. Connection between user and product, between product and product, and so on. All those connections can be exploited for doing different things. For example, building a recommender system on this kind of relation, instead of just traditional collaborative filtering or similar approaches. Another typical use case is frauds. Normally, a fraud is a situation in which different people are looking for an agreement for stealing some money, for example, from a financial institution, and they choose to move together in order to get some advantage. Looking at frauds with the focus on the relation between the people that are involved, for example, in different frauds, is a great plus for improving the anti-fraud system that exists in banks, in insurance companies, and so on. Another typical case is the connection between people and other people. So basically, friends, for example, that have been asked for introducing someone else to some important person. Or similar case in the COVID pandemic, there was a big focus on the connection between different people for monitoring the spread of viruses in the different group of society. All those kind of connection basically part us to think that these kind of information are connected data, and basically we can look at them as if they are graph. So basically going to the theory of graph and everything that is possible in an analytical approach on graphs. Today, what we will do then is do a very brief introduction on the concept of graph with some theory, for moving to the algorithms that are possible to implement on graph. And finally, with some conclusion, we hope to give you some ideas, some possible wrap up for understanding how to use those information in your typical work or typical studies that you are doing now. Before going to this, just 3 slides on the company in which me and Julien are working. That is I don't know if we are actually blocked on the first slide for the people on Zoom. Just let me screen share everything. That is probably better. Okay, let's see there. Yes. No. No. Sorry. Because I show. Okay, sorry for people in the remote. I was not able to see that. Actually, you were not seeing all the previous slide, but it was just the introduction, so probably not a big problem. And continuing on this, me and Julien are working in Data Reply. That, as the name suggests, is one company inside of the Reply Group. The Reply Group is a consulting group born in Italy more than 20 years ago, and now composed of more than 100 companies, or almost 200. Every company is focused on something in particular. As the name of Data suggests, we are focusing on data in the 3 different aspects from our point of view. Big data, so the data engineering part, data platform part, AI and all the analytics, AI, machine learning, data science, and finally quantum, with the idea of using quantum approaches to solving particular problems that require some different way for being managed. In particular, the optimization problem, in which using quantum approaches with Kubo formulation can be a great booster to improve what's possible to get from data. We do this kind of activities across different industries, across different functions. What's important here is that end of the day, we are quite a big group. We are more than 200 colleagues working in different companies. There's Data Reply in Italy, in which me and Julien are part, but there's also Data Reply in Germany, UK, in French. So we are a kind of sub-network inside of the network of Reply. We do this kind of activities since a lot of years. We have almost 100 projects up and running in production. And we can divide those projects in 5 main areas. That is sales and marketing, so analytics that looks at the relation between the customer and our enterprise, or enterprise analytics, so thinking at how to improve the internal process of the different enterprises with analytical approaches, so things like IPA, RPA, computer vision, and so on. Quantum and accelerated computing for all the optimization part, for the physical part, industry and IoT. And finally, the unit in which me and Julien are working, that is data engineering business unit, with also the focus on security intelligence. In particular, security is one of the typical places in which it is possible to use graph for improving the results of the security processes. But going to the real focus of the speech, I will leave to Julien.
Okay, so hi everyone. So let's start with a little bit of an introduction to graphs. I know that some of you already know it, but for the other ones, okay, let's start with the concept of graphs. What is a graph? Graph is a mathematical representation, okay, of complex and connected entities that we can call network, okay? It's quite easy. These entities are represented by nodes. And I already know that you know this thing, but it's very important. So they are the entities, the objects of the real world. And we will see later what I want to say with that. These nodes are obviously connected by links. Okay, they are the connections. In the picture on the right, yes, there is some nodes of a person. Okay, so 2 person nodes and a book, and they are connected with is friend with relationship and as read relationship. Okay, so it's I think quite easy to understand. And we have some labels, so the person label or the book label, and we have some properties, okay, related with the node. So we enrich the node with some information. Okay, the very important thing to understand from this slide is the fact that we don't have a fixed schema. Okay, we are not with tabular data, so we have a dynamic schema. So this is what a graph is. The next question is why to use graphs. Okay, there are 3 main reasons for using graphs. The first one is graph capture interactions. Okay, so it's quite obvious, but this is the first important thing. So we can capture relationships that are sometimes very, very important. So you don't have to waste them. The second reason, and this is very important, they are visual. So you can visualize the algorithms, you can visualize the results. So they are not black box. Okay. And the last thing is they are dynamic. Okay, so you don't have fixed schema, as I said before. So you can work with graph. You can change the question and change the queries. Sometimes with relational data is not possible. With tabular data, sorry, it's not possible because sometimes the information are there on the tables, and if you want to change the problem, change the questions, you have to change the tables. In the graph, you can add the properties, but don't change the structure of the graph. The next question is when we can use the graph approach. In this case, we have 3 main domains. Okay, the first one is the recommendation engine, and it's one of the most famous because and is one of the most important. In this case, we can, and we will see how we can use the graph to suggest some new products to the clients. The second one is, I think, not obvious at all, but in reality, we know that frauds are relational by nature, okay? Because they involve a lot of people usually. And the other important thing is that we can visualize fraud with graphs. And so it's very important for a bank, in some cases, to visualize the fraud schema, okay? The first example, is bill of materials. In this case, we have, I don't know, a supply chain for a certain product that we will see later. And we want to understand the what if, in the sense that we want to change maybe a part of this logistic, of this supply chain, and we want to understand what is the result at the end of this supply chain. We will see some example next. But what are some general domain where we can find some graphs? We have the user bank networks, okay, for the fraud example. We have marketing networks, is some very similar. The third network is the company files networks. This is very interesting because in this case the graphs are not obvious, but in this case we create a connection between the files related with the ontology. The first example is the next example is the internet network. In this case, we have some IP address and something like that. We want to understand if there are some frauds and something else. And the last example is the networks of neurons. I think it's one of the maybe is not very interesting for a company, but it's used, for example, in psychology. So it's a very important example. So, who are the very important players in the world that are using graphs? We have eBay, we have NASA, we have MasterCard, we have JP Morgan, Xbox. And so they are using graphs for several uses. For example, recommendation engine, okay. The knowledge graph. The knowledge graph is a very important application. That is the application related to the connection between files, so the ontology. And in this case, we want to connect the isolated files into a graph network. The next example is for capturing the interaction, the fraud interaction between people. Okay, so in this case, we are talking about MasterCard. And a not very obvious example is for Xbox. So we want to improve the user experience using relationships between players, games, and categories of games. Okay. So now we can start with the very technical part, and we can start and continue with the very technical part. So the question now is how to use a graph to do that. We can use what we know, what we can call as a graph data-driven approach. So the first question is related to the movement. So how things travel through a network, okay? The second question is the influence. What are the most influential points in a network? The third question is what are the groups and the interaction in a network? And finally, we want to discover the patterns in a network. So now we are ready to talk about graph algorithms and how to use them. Okay, we have 5 types of main graph algorithms, and they are related to what we call graph machine learning. We also have graph neural network, but we will not talk about graph neural network today because it's more difficult to understand. So let's start with graph machine learning. In this case, we have 5 types of important algorithms that are community detection. Okay, in this case, we want to detect group clustering of nodes. The centrality importance, so we want to understand the importance of several nodes in the network. We have pathfinding and search that I think it's a quite common example. So we want to find the optimal path between two nodes. Link prediction, that is, in this case, we want to estimate the likelihood of nodes of forming a relationship. And the similarity, that is the last family of algorithms, in which we want to understand what are the similarity between two nodes. Okay, let's move on into the details.
Piano, piano.
Okay, so let's start with community detection. Community detection, okay, as we said, is the family of algorithms where we want to find the nodes that are in a group. Okay, and why we want to do this thing, because we want to find some cluster of nodes, or maybe some isolated groups, or maybe we want to find a network structure. Okay, so we have here three very famous algorithms. The first one is clustering coefficient. In this case, we want to understand if the nodes are very linked together. For example, is a local, for each node we give a local value, okay, that is called the clustering coefficient. And the more relationship you have around this node, the more the bigger is the value associated to this node. So in this case, we can see that, for example, the node number 3 in that is on the center of the graph is related with a very big clustering coefficient. The second algorithm is strongly weakly or weakly connected component. Okay, in this case we have two possibilities, but the idea is to understand what are the island in the graph. Okay, so we want to see how we can divide our graph in some island. And for island, I want to say that is when some graph in an island is not related with some nodes in an island are not related with the nodes in another island. Okay, and the fact that it is strongly or weakly depends on if we use directed connection, so from another node to another one, or undirected. So it's not important the direction, but it's only important the fact that a relationship exists. The label propagation is the very important algorithm, and is related with what we call semi-supervised learning. So in this case, we start with some label in the graph. I want to understand how these labels propagate through the graphs, through the network. Okay, so in this case, we see on the upper part an orange node and blue node. We iterate in time, and we see the final iteration. What are how the different labels spreads through the network? What are the examples? Okay, so this is the one is a real example, and is fraud detection. In this case, we want to understand if some people agree to simulate a fake accident. Okay, so if some people agree, what they do? Okay, they can be involved to fake accident, okay, as passengers, drivers, or witnesses. So in this case, the same people, the same person sometimes is a passenger, some other times is a driver, some other times is something else, okay? And these roles change, but the people involved are the same, okay? And how you can capture this? You cannot do it with a relational approach, but you can use the weakly connected algorithm. Why? Because this person, in a weakly way, they are not connected with the other people in the network, but only with each other. Okay, so this algorithm is the best to catch this pattern. Now we have another very important topic. This is the centrality. The centrality is a general concept to say, okay, this node is important for the graph, but the importance has to be defined. Okay, so we have the first definition, that is the degree centrality. So in this case, we have to see how many relationships are going into a certain node or out of a certain node. So in this case, we can see that the node number 6 or the node number 7 are very central with a degree centrality definition. In the case of between a centrality, sorry, we have another concept of centrality, and is what are the most important nodes for passing the information through the network. Let's take the node number 3 in the central part of the graph. As you can see, it's not very connected to the other points. We have only 2 connections, but it's very important because if you remove this node, you disconnect 2 parts of the network, and so the information cannot pass. So this is a very, very important node for the network. And the third approach that is very important is the classical PageRank centrality. In this case, in my opinion, is an extension of degree centrality, because we are not saying that it's only important the fact that you are very connected with the other nodes. It's also important that these nodes are in a certain sense important in the network. So for example, in this case, you can see that you have the old 6 and 7 nodes that have a PageRank value of 5 and 25.3. Okay, they are in this case, they are important, but we have only we have also the node number 1 that has a very important centrality, because it's connected to some important nodes in the graph. Okay, so in this case, what is the use cases? The use case is the chocolate industry. Okay, so this is an example, but we have some real use cases that we are working on in data reply associated to not the chocolate, but something like that. Okay, so we are working with a supply chain, and we want to understand what are the most important points in the supply chain. So we want to produce the chocolate, and we know that the chocolate is made of several ingredients. Okay, so the recipe is not very simple, so we need some basic ingredients. So the question is, what are the most important nodes so the most important companies, for example, for the production of the final product? Okay, and so you can capture, for example, this thing with between a centrality. Okay, so in this case we can say, okay, if I don't have the chocolate, I cannot do my my chocolate. Okay, it's quite obvious, but you can also say, okay, I don't have maybe a lot of companies that produce milk. Okay, so maybe these some companies associated with the milk production are the most central points. So it depends on your company and on the product. Okay, I will not spend too much time on the pathfinding, but it's because it's quite I think that you already know it, because in this case the idea is, okay, we have a network and we want to start from a certain node, and you want to go to another node, and the question is, what is the shortest path between these 2 nodes? And the path is the set of links between the 2 nodes. And sometimes you have a weight between in these relationships. Okay, and so you can count in this case, maybe, I don't know, we have in blue the shortest path between A and F, and the shortest path is not A, B, D, F, because if you count, for example, the time between these between A and F passing through B and D, this time is more than the time passing through A, C, E, D, and F. Okay, so the shortest path depends on maybe the link or the weight on the link or something else. So, and I think the most important use case is optimal transport. For example, Google Maps, but it can be more than that, because sometimes you can transport some goods, okay, from a similar customer, and maybe you want to optimize the fuel from to to transport these goods, so passing through some customer in order, okay? And maybe you want to optimize the path that a certain the path that has to be taken to move the goods. But I think the new part for you is the similarity, because it's not very obvious. In this case, you are what you can do is to understand how two nodes are similar according to relationships. Okay, so the first similarity that we can see on the left is the Jacquard similarity, that I can call as a set similarity. So in this case, we have, for example, Julien, me, and Marco, that is not there, and we like some movies. Okay, for example, I like Toy Story. Yes, okay. I also like Matrix or Titanic, Star Wars, and The Good Father. And the question is, do we like the same movies, or we have similar tastes, me and Marco? Okay, we can count how many movies we like, we both like, and with respect to the number of movies that we have seen. Okay, and in this case, for example, we like 2 movies. We both like 2 movies, and we have seen 5 movies. So the Jacquard similarity is 2/5. Okay, it's quite easy to understand. But sometimes maybe we have seen the same movies, but we don't like it. We don't like them. Okay, so sometimes it's not important only the fact that we have seen some movies, but also the rating associated to these movies. So in this case, we can take the rating that we gave to some movies, okay, and we can compute the Pearson similarity, so a Pearson correlation related to the ratings of the movie or the movies that we have seen. What is a very common example and the first starting point in for a graph approach? What I want to say is the similarity is the starting point to create a recommendation engine. Okay, so this is the very starting point. You create a similarity graph. Okay, and it's very important to recommend a product. So if you have the same interaction between you and some other user, or you and some products, okay, you can maybe have the same tastes. You can suggest with this simple information some products, and it's very interesting because I'm working on a recommendation engine using graph, for example, for a competition, a Kaggle competition, and I'm working with a new type of recommendation engine that use, for example, some graph algorithms that we have seen before. So in this case, we want maybe cluster some people together, and we want to, for example, suggest the products in the same cluster. And to create the graph, we start with some similarities between the nodes. Another important example of graph algorithms is the link prediction. So in this case, the link prediction is, okay, now we have a certain type of graph, but this graph can be dependent on time, because, for example, when you are, we have a network of people with a friend relationship, okay? So this, the friendship depends on time. It can change. For example, when we want to understand what is the probability that, for example, A and D will become friends. Okay, so with the first approach of using the common neighbors, we want to see how many common friends they have A and D. So in this case, you have C and B, and so the more friends they have, the higher is the probability then they will create a relationship. Okay, but the Adamic adder say, okay, the common neighbors is a very good approach, But in general, the fact is that if you have a friend with a lot of other friends, maybe this friend will not present you. Maybe he will present another person. Okay, so the probability to connect to connect a certain person to another one depends on the number of neighbors